I did some coding without recording that. Not really any new language features, but I basically just looked at making Plum more robust. And the way I did that is by adding ways to interpret the individual compiler stages. So Plum compiles using a couple of compiler stages, and previously you would just run the entire compilation pipeline, and if something doesn't work, then in the end you get some bytecode, and that may segfault, for example. Of course, that's usually not the case, and the compiler emits and shows nice errors for most of the errors that you can do. But sometimes, if there's a bug in the compiler, then you would only learn about that right at the end. So, in order to make bugs more easily discoverable and be more confident in the compiler working and doing what it's supposed to be, I basically added interpreters for some of the intermediate stages. So now there are these files for running Yogurt directly. Yogurt is a compiler stage in here with a couple of operations that can switch on an enum, for example, or create a closure, or access a struct member or something. Now I have this run Yogurt interpreter. It's not really big, it's like 200 lines, but it basically just has a notion of what is a value at the abstraction level of the Yogurt. It can be a byte, it can be an int, it can be an array of other values, and so on. And then there's, after the printing, there's a way of running the Yogurt, which just runs the entry point, and the entry point is the name of the main function, basically. And running a function runs the function body. Well, running the function body actually runs the expressions within the body, and those then do stuff. So, for example, accessing the member of a struct gets the struct value, and then just gets the member there. And the way that works is that during this interpretation, we keep track of the visible variables, which is just a map from the Yogurt IDs to the values that are defined up here. And we also keep track of the stack so that we can display nice error messages and kind of visualize the execution of the code. Yeah, and that's enough to execute Yogurt code directly. Which means that now you can just basically execute the first part of the compiler pipeline up until here, and then just run the program directly and see if it produces the correct result. And if it does, then you know that if there's a bug in your code, then in the compiler, then the bug has to be somewhere after the Yogurt. Now I did a similar thing for the pesto and the waffle and the ground. So for example, in the waffle, we only have, all data structures have been memory layouted. So here, rather than having a separate notion of a waffle value or something, we just pass around slices of bytes. Every single expression, evaluating that results in a slice of bytes, because that's the notion of abstraction in the waffle. And in the pesto, similarly, where we have, only pointers and structs and enums, I think. Yeah, and primitive types like byte int. We no longer have any sort of lambda in here. Yeah. And the cool thing about having these intermediate compiler stages is that I can more easily add more debug assertions in there. For example, for every heap allocation, for every pesto value pointer that we have, we also just track the reference count and whether that value has been freed. And then when you free a value, actually we just, hang on, can I see that? Here. Yeah, we check that the reference count is 0, for example, that that the type matches, that it hasn't been freed already. Hang on, no, we don't track that. but for buffers at least we do. Yeah, we check that we don't free things twice. And when accessing data by loading that or storing something there, we check for use of the freeze. So the idea is that running, like interpreting these intermediate compiler stages not only gives you a result, but during that computation it also dynamically checks all of these invariants that the compiler stage is supposed to adhere to. So you can be really confident that, first of all, your program compiles, but also that it doesn't just work accidentally for this input, but that it really respects all of the requirements from that compiler stage. And this actually caught a couple of bugs, like having these, checks that reference counts match, that the types match, that, for example, if we load a pointer, then we check that the actual type of the heap value, that it matches the type that we're trying to load. This is, of course, totally inefficient for real execution of programs, because now every heap value also tracks whether it has been freed, what's the type of the expression is, and so on. And we don't want that for like the final code that you're running. But for these intermediate compiler stages, this is super good at catching bugs. Yeah, so let's maybe quickly go through the Git history. Yeah, basically I added these interpreters for the intermediate stages, like running the yogurt, for example, running the pesto, and so on. And then I fixed a lot of bugs, just like here, freeing. I think for enums we tried to free the, if we had a recursive enum, that would then do heap allocations for the payloads, and those were not correctly freed. Something along those lines, where the size of the memory that we tried to free didn't match the size of the memory that we allocated. That is fixed. Yeah, a couple of other fixes, like iterating over arrays was broken. Some use after freeze, and yeah. The main point is that the compiler is a lot more robust right now, because I fixed a lot of these bugs that were caught by having these intermediate checkpoints in the compiler that run the intermediate representations in a very strict way. Yeah, actually I don't want to do any programming in this video, just wanted to mention that this is what I'm doing. I can maybe run the program, an example program that I might also show. So this is the example program. Let's remove that. Oh, a couple imports, a lot of them unnecessary. But the main point is that this is the main function that has this type loop. Oh, hang on, we do need that, which is an array of ints. And the built-in type info function takes a type and gives you information about that type. And then we format that type info information. So in the standard library, we can see that type info, this type info function is imported from the build-ins module, which means the compiler kind of magically implements this function. And this returns type info, which is this giant enum that tells us whether this type is a byte or an int or a type or an array of some other type, etc. So for our type here, which is an array of ints, that would be, well, just a type info array, this variant, and then it contains type info int. And formatting that, formatting an array, for example, just builds a string that contains array of and then the item type, which means when running this program, this just returns the string array of int, allowing you to kind of do type reflection or to kind of get type information at runtime. Yeah, so let's run that. So yeah, after compiling the program, you can see that a lot of stuff is being printed, and that's actually the output of running these compiler stages. So here we build the yogurt, and then we immediately run that. And this is also like really nice for debugging. We see that the main function is executed with the argument 5. And this then calls the format function. This is the function name with this argument, array of int. Apparently array of int is like inlined during compilation. And well, that calls, format of int of the inner type. That returns us a string. And this is probably int in ASCII. And then we call plus of that string and I don't know, what is this? Probably opening parentheses, array, and then space. Yeah, 32 is a space. And this concatenates strings and this does stuff. Yeah. And in the end, the result is array of int. Then we compile that to the waffle, we optimize that, we run the waffle, which also results in array of int. Then we compile that to ground, we run that, also results in array of int. So all of these intermediate compiler stages, they produce the same result, which is to be expected. And finally, we serialize that to bytecode to this playground.ground file. And we run that in the ZIG VM and see that this indeed returns array of int. Yeah, I'll probably comment out these, running these intermediate stages, because this is useful for, if you have a bug and you want to find that. Running those gives you confidence, but otherwise it's just unnecessary output. Yeah, I think that's it for this video. In the next video, I have a much more robust compiler that I can work with, and if I do introduce bugs in the compiler that break things in mysterious ways, now at least I have a way of pinpointing that and kind of being sure in which part of the compiler that bug is being introduced. So see you in the next video. Bye.